although there are certainly times when a probability can be pretty straightforward, like rolling a die or pulling a card from a deck of cards, most probabilities that we're trying to find are probabilities of compound. So sometimes I like to think of it as like how many events go into a successful launch of a spaceship. I mean, talk about compound events. I mean, you know, it has to be engineered right, it has to be built properly. Each one of tens of thousands of pieces have to be made just to perfect specification. The weather has to be right. I mean, there's a real good example of a compound event, and one that we would certainly want to know what's our probability of success on that. Well, we probably won't get into analyzing any probability that severe, but there are two kinds of probabilities that we want to talk about right now: independent events and dependent events. Now, there are some examples on your handout, but independent events are events that don't affect one another. So, something like, if you have an apple for lunch is one event, and if you stumble walking up to the second floor, that's another event. And I would say it's quite likely that those are independent events. Those do not really have anything to do with one another. Example that is on the handout is I have 12 little tiles, each with a number on it, and I'm going to pick one, and pick a number between 1 and 12. And then I have a spinner that has 6 colors on it, and I'm going to spin it and it's going to land on a color. Well, those really have nothing to do with one another. What number I pull out on the tile isn't going to have any effect on the color that I pull out, and the color that I select isn't going to have any effect on the tile that I pull out. Or, another example, I'm going to roll 2 dice. Well, this one may come up with a 6, and this one may come up with a 5, but those are totally independent of one another. The fact that this one rolled a 6 and this one rolled a 5 has nothing to do with one another. This one could have rolled a 2 and that one could have rolled a 3. Nothing to do with one another. Those are independent events. We also have dependent events. So what would be an example of a dependent event? Let's say that you come to school out of uniform and you get a uniform violation. I would say those are dependent events. You might come to school out of uniform and not get a uniform violation. Or you might come to school in uniform and not get a uniform violation. Those are dependent events. Another kind of dependent event, maybe make a little more sense. Here's a picture of a full deck of cards. And let's say that I reach into this deck of cards and I randomly select the 4 of clubs. Well, I will tell you there are 52 cards in a deck, and so my probability of pulling the 4 of clubs was 1 in 52. Now I take that 4 of clubs and I put it in my pocket, and now I'm going to draw another card, and I pull the 8 of hearts. Well, the fact that I pulled the 8 of hearts, that was a 1 in 51 probability, because the 4 of clubs was gone. So my probability of pulling the 8 of hearts was dependent on the fact that I had already pulled the 4 of clubs. So it's very important to decide whether the events that you're analyzing for probability are independent or whether they are. This is an extremely important rule that will serve you well in many situations, not just on your SAT or in this class. It is the multiplication rule for independent events. And what it says is if I have event A and I have event B and they are independent, then the probability of A and B both happening is equal to the probability of A times the probability of B. Let's walk through an example. You have 2 6-sided dice. One is red, the other is green. What is the probability you will roll, an even number on the red and a 1 or a 2 on the green. So first of all, whatever we roll on the red, we kind of talked about this just a minute ago, whatever we roll on the red is independent of what we roll on the green. Whatever we roll on the green is independent of whatever we roll on the red. So we have two independent events. The probability of rolling an even number on the red, which I write in proper probability notation, P red even, is 3 out of 6. There's 6 numbers on the die. 2, 4, and 6 are even. So that's a probability, or in decimal form, 0.50. The probability of rolling a 1 or a 2 on the green die, so again in proper notation, P green 1 or 2, is 2 out of 6. Remember on the dice I have 1, 2, 3, 4, 5, and 6. My favorable outcomes, there's 2 of them. The total sample space, there's 6 of them. That gives me my 2 out of 6, which I can simplify into 1 over 3, or in a decimal form, 0.33. So the compound probability, remember back to our word back here, the compound event, the compound probability of rolling an even number on the red and a 1 or a 2 on the green would be P red even and, because I'm doing both of them, I'm doing the red even and the green 1 or 2, would be the 1/2 times the 1/3, and that equals 1/6, or 0.167. Note the format. P event A and B is equal to PA, whoops, whoa, don't do that. P of event A, come on, stop it, times P of event B. A, B, you can't see what I'm doing. Let's just take another example of something that you might see in class when I'm using the magic bowl of probability, which has all these different sticks in it. So let's say that there are 20 students. So 20 students, and each has 1 stick. And I pull a particular student out. So the chance of my pulling any particular student out is 1 out of 20. And then I put the stick back in to the bowl, and I'm going to pull another stick out. Now, these are 2 independent events. I took the stick out, I replaced it, there's the same 26 in there, I mixed the bowl up, I randomly reach in, and what do you know? I pull out the exact same student, a 1 in 20 chance. Chances of that happening, the probability of that happening, 1 in 400, which I can't do that in my head. I should be able to. 1 divided by 400. That's a pretty small probability. That probability is 0.002075. It's a very small probability. But you know something? Happens all the time. 2 independent events using the multiplication rule. 1 over 400 probability. Now what happens if the events are dependent? Well, if they're dependent, then the probability of both of them happening, probability of A and B, is the probability of A times the probability of B after event A has occurred. That's how you write it. So this means the probability of A and B is found by multiplying the probability of event A times the probability of event B after event A has occurred. An example. Here's my deck of cards. 52 cards in a deck, 4 different suits. Suit is hearts, diamonds, clubs, spades. 13 cards in each suit. 4 times 13 is 52. So I want to know what is the probability of picking first the 2 of hearts and not replacing it in the deck, but then picking the 3 of spades. So I reach in and I select the 2 of hearts. That probability is 1 in 52. And then I say, well, okay, now I'm going to reach in and I'm going to get the 3 of spades. Well, that probability isn't 1 in 52 anymore because I didn't replace the 2 of hearts. That probability is 1 in 51. The 2 events are dependent on one another. I'm saying I'm not getting the 3 of spades until after. So the similar multiplication, it's really quite similar. And I'm going to have probability of event A times the probability of event B after. So I have 1 over
Very close to